Good afternoon, glad to see everybody. My name is Kyle Mayborn, I'm a geology professor. I also do some undergraduate research coordination for the college. So on behalf of the College Department of Sciences, I'd like to welcome everybody to the 2019 Roger and Jean Morrow Lecture. I'd like to thank the committee who not only worked on the Morrow Lecture, but also worked on today's Natural Science Research Symposium. So I'd like to thank Dr. Brian Ballett and Dr. Rich Musser, Dr. Ken McCravey, Dr. Sudha Malor, and also Dr. Vanessa Cooper for all their efforts towards this afternoon's activities. And with that, I'm going to give it over to Dr. Musser, who's going to talk just briefly about the Morrows.
Take it. This is a reminder, at the end of the Morrow lecture, we will have announcement on the awards for the posters. Again, I'd like to thank Dr. Cooper. She started with us this fall, and she's been a wonderful department chair, and she was very involved with helping us with the Morrow lecture, so thank you, Dr. Cooper. So I've had the privilege of getting to see quite a few Morrow lectures. If you're not familiar with the history of the Morrow lecture, it's been a lecture that goes from the biology department to the physics department to the biology department to the physics department. And each year, we get to bring in a wonderful speaker. We've had National Academy of Sciences speakers here, like May Berenbaum from the University of Illinois, so we had some excellent speakers. Just to give you a little bit of the history, and thank you, Kyle, for putting this together for me. Roger and Jean Morrow endowed this lecture series and a number of generous scholarships in 1983. You might know there's a Morrow scholarship as well. The Morrows came to Western in the early 1960s, and during their 20-year career, Roger was the chair of physics and Jean was a Falcon member in biological sciences. They both had a passion for pursuit of scientific knowledge and knew the importance of bringing outside speakers to the departments, and thus they endowed this lecture, which now bear their name. So this is their legacy, and we're so thankful to get to be able to do this. Dr. McCravey was our co-Morrow committee member and chair, and he's going to introduce this year's speaker, Dr. Kishor Kapale. Dr. McCravey. Thank you, everyone.
It's a real pleasure to introduce Dr. Kapale, our 2019 Morrow lecturer. Most of you probably, a lot of you probably know Dr. Kapale. He's the interim chair of physics and professor in the physics department. Give you a little background on Dr. Kapale. He received his PhD in physics from Texas A&M University in 2002. Then went on, did a postdoc at Princeton University. He then got a very prestigious position with NASA at the NASA Jet Propulsion Lab at Caltech. He then came to WIU in 2007, and since then he's really had a tremendous impact on our university, teaching, service, research. He's been very involved in STEM research or STEM education of youth. He was a co-founder of the Graduate Research Conference, where our graduate students give presentations on their research, and he's received awards for his service, for his research. He's been very productive as a researcher. He's published over 40 papers. He's given roughly 90 presentations at scientific meetings and seminars and so forth. So very productive. He, matter of fact, he's been recognized earlier this year for his contributions to the university. He was chosen as a distinguished faculty lecturer, which is, I think, the highest award that a faculty member can receive here at the university. His main research focus is quantum optics, and his research, a lot of it is very interdisciplinary, and he's going to tell us about some of the ways in which his research relates to biology in his presentation today. So
Dr. Kapale.
We need to keep things cool before I start talking. So, I appreciate this honor, accidental honor, if I may call it, but it's kind of fitting that I get to talk about connections between biology and physics, and especially applications of my area of quantum physics, which is really quantum optics. And I will tell you in a little bit what it is, to the field of biology, given that this is a Morrow lecture which is endowed for physics as well as biology. So thank you, Professor McCurry, for the flattering introduction. Again, I'm honored and humbled to talk to you about this quantum biology, so to speak. I will give you a very brief history of it a little later. It is as old as quantum mechanics, the thought process itself, but the actual interesting work has been happening only in the last 10 years or so. So very new field. If biologists, you're not afraid of learning quantum mechanics, there may be a fantastic opportunity for you to get into this new field. And physicists, of course, you should learn a little bit biology. I did not, and I keep dreading that fact every time I look at these things. So let me make sure my pointer is working. Okay. All right. I am dealing with some technology issue here, but let's hope everything will work out. And you see water, right? Water is very important for biology. So there has been a lot of excitement and speculation that nature may be using quantum mechanical practices. And to some extent, it's not surprising. We'll talk about that here in a little bit. But for the biologists in the audience, I'm sure all of you have studied physics here that are in the audience today. Yes or no?
Mm-hmm. Yes.
Okay, very good. So let's take a look at quickly at the dictionary definition of physics, and then I'll tell you that it's not quite correct. The branch of science concerned with nature and properties of matter and energy, and this is what we will be dealing with today. The subject matter of physics, distinguished from that of chemistry and biology, includes mechanics, heat, light, other radiation, sound, electricity, magnetism, and the structure of atoms. So if you're a biology student, the entry-level physics sequence that you take more or less covers all of that. It doesn't go into the subatomic physics, which is what you need for what we're going to talk about today, and so I will point out the connection. Another important thing is, it's not just about the properties of matter and energy, it's actually about interaction between matter and energy, how we get them to essentially talk to each other, and how we distribute energy among the different matter particles. And that is what it is about. So let's take a quick survey. This is just for me. I'm not trying to judge you. I'm just trying to find out where my audience is, because I'm not a biologist. And so I need to know how much you are already familiar with. So biology students, please raise your hands so I get kind of a head count of how many we have. Okay, very good. Now, oh no, hold on. You don't get to put your hands down yet. Keep them up, okay? Please lower it now if you have studied quantum mechanics. Well, that's good. I'm impressed. So I just had now 2 or 3 hands up. And remember, I've been studied quantum mechanics, not just kind of peripherally read about it in Scientific American. That's not what I'm asking. Okay, let's now ask the same question to the faculty. Please raise your hand if you are a biology faculty. So we have quite a few here. That's good. Thank you. And now you can lower it if you have studied quantum mechanics. Okay, very good. So that means lots of work remains to be done, right? I need to explain some of the basic quantum mechanics based on where we are. And so I will do that in the beginning, and then we will connect it with biology. So what is quantum biology, since I'm talking about it? There is no dictionary definition for it yet, okay? So that tells you it's a new area, exciting time to get into it. This is kind of a rough definition that people have put together. I have my issues with it, but let's not go into that. Quantum biology refers to applications of quantum mechanics and theoretical chemistry to biological objects and problems. Okay, so that's what it's going to be. Many biological processes involve conversion of energy from one form to the other that are usable now for different kind of chemical transformations, and you biologists know a lot about this than I do. But it turns out these processes are inherently quantum in nature, and biology has to display eventually that quantum mechanical nature in its manifestation of how these things work out. And that's what quantum biology is all about. Just a very brief history. Like I said, it is as old as quantum mechanics itself. Our idol for quantum physicist Niels Bohr, 1929. Here's a excerpt from one of his lectures, which I will just quickly read for you. The development of atomic theory has, first of all, given us a recognition of laws which cannot be included within the framework or frame formed by our accustomed modes of perception, which is basically talking about classical physics, if you will, and I will point out some of the differences here in a little bit. The lessons we have learned by the discovery of the quantum of action. Now we don't need to worry about what it really means. Let's just pay attention to the word quantum. Opened up to us new prospects which may perhaps be of decisive importance, particularly in the discussion of the position of living organisms in our picture of the world. So very prophetic at that time, 1929, just 2 years ago, people had kind of understood how to use quantum mechanics to calculate things. So very, very prophetic, and it seems to be playing out, as I will point out. 1930, Pascal Jordan coined the term quantum biology, German, so I use the direct German word, die Quantenmechanik und die Grundprobleme der Biology and Psychology. So he was already connecting quantum mechanics with biology and psychology in 1932. First paper, if you can call it, in quantum biology, 1943. He wrote a book, Physics and the Secret of Organic Life. A year later, one of our other celebrated quantum physicists, Erwin Schrödinger, wrote a book, What is Life? I actually have a Dover copy of the book with me, somewhere in my bookshelf. So the Jordan's insistence that living organisms have a unique ability to amplify the quantum. Okay, that's what the gist of the talk today is. Into the macroscopic world does have a lot of resonance now with the modern view of quantum biology. Quantum biology did not really pick up for quite some time, maybe because of Pascal Jordan's connection with Nazism and his sympathy to them. That may be part of the historical story that I will not go into because I don't know much about it. So advertisement for quantum physics. Stars, how stars emit light. There's tremendous amount of quantum physics. How all these semiconductors in all of your on your gadgetry, mobile phones, tablets, computers, laptops, all of chemistry, at the basic of it. Photovoltaics, the new type of LED lighting that you may have in your houses, some macroscopic quantum phenomena, which I will demonstrate for you here in a little bit, superconductivity that allows us levitation and propulsion, maybe in future, nuclear physics, and a couple of new ideas, and this that are coming up, which is humans themselves. The picture actually has nothing to do with quantum. It is taken from a series on Amazon, kind of a sci-fi series, and they also have Humans 2.0, if you can enjoy the pun there. And of course the birds, and I will talk about the birds in quite a bit in detail. The way they navigate, it turns out, relies heavily on quantum entanglement, which is very, very sort of a modern concept in terms of its usability, the utility of it. The concept itself goes back to Einstein and even Schrödinger, but we won't go into that. So that's just the advertisement for quantum physics. Size scales, of course, for biologists, you are comfortable with this. 20 angstroms, atoms, this is what I do deal with on a day-to-day basis, atom-light interaction. during my PhD work, I studied Bose-Einstein condensate, which happens to be here 2 years before I started graduate school, 1995. Molecule of the year. Okay, so chemists in the audience, that's molecule of the year because all of these atoms, behave in unison. Have some collective modes that you can call them as molecules, and that's 20 millionth of a meter. So that's a jump of about 6 orders of magnitude size scales for quantum effects to be seen. Interesting thing though is I would not be here if these were the only quantum phenomena that existed. This is already macroscopic, if you can call it that, about 1,000 atoms when they initially realized Bose-Einstein condensate in lab. Now you can have about 1 million to 10 million atoms in BECs and hold them together in the same quantum mechanical ground state. So there are several actually macroscopic, and macro I mean something that our eyes can see. Okay, so macroscopic quantum phenomena, again very vague definition, but that works. Superconductivity, superfluidity, Bose-Einstein condensation, which is a molecule that we talked about, and this little laser that I have, it's a macroscopic quantum phenomena as well. So let's take a quick look at what is possible with macroscopic quantum phenomena. You cannot be you cannot do science without liquid nitrogen, right? Dr. Monson knows that. And so here we have a little magnet. On the magnet, we have a little pellet, ceramic pellet of, for chemists in the audience, yttrium, barium, copper oxide. That is prepared for me, I think 2-3 weeks ago by Dr. Malur and Dr. Babu in their lab. And I have several of them actually sitting here. Let me see if I can show you. Sitting here in liquid nitrogen. You can see a little bit of a bubbling there. My hands are shaking, sorry about that. Okay, you can see the bubbling now. So some of them are sitting there. So nothing remarkable over here for that pellet that's at room temperature. It is sitting on a very powerful magnet, but nothing really interesting. Now let's hope it has cooled enough for us to see the magic of quantum mechanics. Okay, that did not quite do it. What you're looking for is a little bit of a magnetic levitation going on. Okay, that one, I think settled down now, angle wasn't quite right. Let's try again. The samples are about a month old, and I think that's kind of about their life, but let's hope it works.
It's
My
working.
computer decided to sleep. So let's try again. Now, the thing with demos is it may or may not work.
It's kind of
You
working.
see it floating? I think it's
spinning.
It was floating for quite a bit. You see kind of whitening of the top part before it settles. Let's try one more time. Makes it difficult with my hands. Okay, there, now it's settled, so I think I moved it a little bit. But so what's going on there is when you put this, when the samples are cooled to liquid nitrogen temperature, they behave as superconductors. That means they can allow currents to flow through losslessly, and those currents then are opposing the magnetic field on which they are sitting. And so you get essentially balance, these two opposing magnetic fields balance the weight of that little pellet, and that gives you magnetic levitation. But it's happening at the distance scales that we can see, and that's the interesting part about it. Let's go back. Okay, so let's look at some of the interesting features of quantum mechanics very quickly. Classical reality, which we are all familiar with, is very crisp and crystal clear. Example in point, and this, if you were at my DFL, you know about this. Last month earlier, SpaceX flew Dragon, one of the private space vehicle, to dock with the International Space Station. Possible because classical reality, once you know the initial conditions, you can calculate you can throw a dart at a moving target that's about 254 miles away from the Earth. So very, very interesting. Quantum world, on the other hand, is fuzzy. Now, of course, pictures taken of fast-moving objects with your cell phone camera are fuzzy too, but there is a room for improvement there. That's not a technological limitation. That is just because of technological limitations, rather. In quantum world, it is inherent. No technological improvement is going to get you there. Here is a little puzzle that the Heisenbergs are facing. Lady Heisenberg cannot find her keys. Herr Heisenberg says, you probably know too much about their momentum. And so that means there is an inherent uncertainty principle that says you cannot know the position and the momentum of a quantum object at the same time. For us, for the quantum biology, it turns out it's the other complementary pair of variables, energy and time, that are important. You cannot know the energy state of a quantum state and at a given time with precise accuracy. There is uncertainty in that, and that is very useful. And that's called Heisenberg's uncertainty relation, if you will. Energy in general in the quantum world comes in indivisible packets. We have to talk about energy because physics, even at the classical world, at the classical scale of things, is a study of energy. And in the quantum case, it behaves differently. Just to give you a couple of classical examples where things come in discrete packets or in discrete jumps, if you will, music notes. You have nothing between E and F on, let's say, the highest string there. Here is, kind of an ironic name, little giant quantum ladder. If you cannot be stable in between the rungs of the ladder. You have to be on one of them, and that's just gravitational potential energy that's going up as you go up. And similarly, the electron in an atom or electron in a molecular state has a discrete set of discrete energy levels. These rungs, if you will, are not equidistant like in here. Here you want them to be equidistant for convenience. Here nature gives you them that way, and you can't really do much with it. So these energy ladders are going to be important. I'll be showing you quite a few of them. If you are a theoretical chemist, you are comfortable with pretty complicated structures. For me as a theorist, we theorists like to study, if you will, spherical cows, as simple a model as you can build, so you can study any given phenomena with its finest details with one variable tweaking at a time. And for me, the maximum I have worked with is about 7 or 8 energy levels together, and that calculation gets crazy very quickly. Another very, very important feature of quantum mechanics, or the microscopic world that we need to worry about, is the so-called wave-particle duality. In general, since we are talking about energy, there are two modes of energy transfer. One is through waves, where it's already kind of spread out, but still can move through space. Particles, you have localized package. Imagine a gold ball that I throw at you. The gold ball is moving through air, but at any given instant, the energy is contained within that gold ball. And it turns out, light, of course, we know as a wave. It turns out, so are all of these microscopic particles, electrons, neutrons, protons. You can get crazy and have about 60 atoms together. That's what these buckyballs are. And molecules containing even 100 or so atoms, they have shown that these, which you would normally consider as particles, show wave properties. So when you go to the quantum world, there's a clear mixing of these two ideas of particles and waves. You can't tell one from the other unless you do some very careful experiments to figure out what's going on. We won't go into the details of that today. So light as a wave, just kind of a little simulation. We don't need to go into the details there. Interesting thing to note about waves is when you add them together, it's not always 2 + 2 = 4. Sometimes it is when the waves are in phase. So the peaks here are matching, so they would add up. On the other hand, here the peak is matching with the valley. They're going to cancel each other, and you get that. And of course, I can quickly show you a little demo of that. I have an even brighter laser pointer, which behaves well. Okay, so that's what that is up. Let me make this black so you can see it. And I have just like just like the picture here, you have a light source that is now blocked by a screen with two openings, and so basically you have two independent waves that are essentially driven by the source, and then they are falling on the surface. As the distance traveled by these two waves at any given point on the screen may be slightly different. They may come up at some locations, add together. At some locations, they would cancel each other, and you get bright and dark region. You actually get a variation, continuous variation in the intensity. But that's kind of what we are trying to simulate. And it's interesting that you can actually do this you don't have to get into the darkened room in a lab to do this. I can show it to you now. So I have those two slits here, and I'm going to shine my laser pointer on it. So it's a slightly thicker laser pointer, as you can see. Makes a much brighter spot on the screen. Everybody sees that? Now let's see what happens. What do you think I should... I need to be careful there.
Wow.
So everybody sees that interference pattern?
Yep.
Dark and bright fringes. Okay, how many of you have seen that before?
No, I saw your lecture before.
Okay, so about 1/3 of you, that's good. That means some of you saw something new today. So that's good. Okay, so that's interference. And it's actually very easy to do that with these green laser pointers in front of the audience. Classical particles, it turns out their wavelengths, the quantum analog of their wavelength, something called a de Broglie wave, which I will point out a little later, is extremely small. And so if the distance between these two slits is larger than that wave, and that's what we normally expect for classical particles, wood balls thrown through two doors at once, you will get two heaps on the other side. Quantum particles, on the other hand, you get a pattern form. And this interesting thing about this is whether I'm doing the experiment with laser or with individual particles, they have done that for electrons, neutrons, and so on. It works. Interesting thing is it works even when only one particle is in the apparatus at a time. That means the particle is not giving you this interference pattern because of the presence of the other particles. It doesn't even know that there are other particles there. It is happening without any interparticle interaction. That means the particle must be interfering with itself. So particle by itself shows that wave character. It has this possibility to go through two doors at once. And in some sense, here's what you kind of see. Let's let it go through one more loop. So you will see that pattern building up over time. Initially, kind of random, more or less uniform distribution when one particle is coming at a time on the screen, but over time it builds up. And so that is something very, very interesting, very, very intriguing. It's something that has puzzled physicists for quite some time. Particles interfere with themselves. Okay, so the de Broglie wavelength that I talked about, water waves, about 3 meters. Now, it depends on what is the speed of all of these objects, but extremely small. Normally, it is given by h over mv. So, smaller the speed, larger would be the de Broglie wavelength, and of course, mass. Larger the mass, smaller would be the de Broglie wavelength. And the smaller the de Broglie wavelength is, it would be very difficult to do, for example, interference experiment with apples. That's not going to work. That's the reason for it. Okay. So let's talk about superposition. So now what's going on there? So again, I'm throwing terms here. These are terms that you can look up and know more about them. This Miss Photon, for example, in our double slit experiment, is confused. Which way does she go? She's kind of in a superposition of being at the, going through both of those windows at the same time, and eventually that ends up with that interference pattern. That superposition idea becomes very, very useful for some of the things that we're going to talk about later. But for now, I want to change gears just a little bit and talk about one of the very classic quantum phenomena called quantum tunneling and discuss its applications to biology. So it is a combination of two important things that we have talked about, the wave-particle duality and the Heisenberg's uncertainty principle. And here we deal with the energy-time sort of uncertainty principle. So normally, if I have a ball here and I throw it at the wall, what do you think is going to happen? Throw it. It's going to reflect, right? Essentially get bounced off of the ball. Do you think somebody standing on the other side of the wall will be able to catch that ball. Let's say I throw maybe million balls from here. Would there be a possibility of the person on the other side catching at least one of them? Not possible, right? Something that doesn't happen in the classical world. Quantum mechanics does allow that kind of a thing to happen. And before I explain this to you, actually, I'm going to jump the slide and show that happening to you. So imagine that's the wall, okay? And here is a quantum particle that's shown as its carrier wave. So let's give it a time. It's hitting the wall. There is a larger probability of it being reflected, but you see the little wiggles going on the other side. Those are probability waves. That tells you can calculate the probability of the ball passing through that wall. Like the wall is thin enough, you will have appreciable probability of that ball going on the other side of the wall. That's called quantum tunneling. There are, of course, several conditions to be followed. If this is too thick, the probability goes down and you don't get anything appreciable going on. And so a very interesting application of this in physics, which is commonly used, we have one similar instrument in our physics lab, Dr. Broglie's lab, which, although it's called atomic force microscope, but part of it behaves this way. So what you really have is electrons in these tips, tiny tips, that are sitting on a sample, and the sample could be a surface of your computer hard drive, for example, which has these arrangement of magnetic material that can be used to record data. And so you have with this tiny tip, the tip is actually not touching the surface, but if it is getting close enough to the surface, there is in some sense now a wall. Electrons don't like to pass through the free space, but if you get them close enough, they can jump and give you a current that is proportional to inversely proportional to the distance between them. So when this tip is sitting right above the atom, you get larger current as opposed to in between the two atoms, and you can actually map the surface of a hard drive or anything that's really fine at the atomic scale. And that's what tunneling allows you to do, but that's a standard physics application. Let's see where it applies in quantum scenarios. And of course, this is now quantum chemistry, if you will. There you have electrons that can tunnel. And so imagine a reaction. Your reactants are sitting over here, and the products are here. In general, because the reactants have more energy, you should be able to go to the more stable state. All physical systems like to stay in a stable state, energetically speaking. So if you plot energy versus something here. So this is stable, but it turns out there's sort of a hidden wall here. Unless the reactants are given sufficient amount of energy, they're not going to do this. For example, take a look at a bowl of sugar. Sugar basically is just carbon, hydrogen, and oxygen. It should get converted into carbon dioxide and water, but doesn't happen spontaneously because there is that energy barrier. Now, if we bring in catalysts, which are in our body, when you consume sugar, we have enzymes that act as catalysts and that allow the sugar molecules to make this jump. So, if without catalysis, these reactants would need to go up and jump up to that level, and then they can fall on and complete the chemical reaction, if you will. You bring in a catalyst which help the reaction, then the wall that needs to be jumped is little less taller, but still there is a wall to be climbed. And in most cases, it turns out tunneling helps the reactants tunnel through here and come to the other side. And most of the enzymes in your body act as catalysts. They are aided by electron tunneling through these kinds of processes. So this is a chemical energy diagram, if you will. Again, remember I told you I will be using these energy ladders of electrons very so often. It turns out other biochemical redox reactions like photosynthesis and cellular respiration also use this electron tunneling. There is another form of tunneling called proton tunneling. Now you may see where is proton coming in here. Remember in chemical reactions, hydrogen can easily give out an electron, and then what's left behind is proton, right? So it is a nucleon, but you can use that. And it turns out So here's, for example, A and T, so DNA, and now biologists know about DNA a lot more than I do, so you will probably recognize that by just looking at it. You have hydrogen here and hydrogen on the other side. This is A and T, adenine and thymine base pairs. It turns out there is a proton can tunnel and go to the oxygen on the other side, or same way you can have this hydrogen can tunnel and go through that. There is the tunneling here happens through something called a hydrogen bond. These A and T base pair are held together by something called the hydrogen bonds, which is hydrogen interacting with some other elements like oxygen here, nitrogen here, without really giving away the electron. So the electron is shared, sort of like a covalent bond there. It is interesting because now hydrogen has only one electron to share, but it is also chemically bonded with something else on the other side, and that's why it is a little bit weird. It doesn't have two electrons to have two bonds at the same time. But what happens is once both of these protons have tunneled to the either side, you get sort of A star and T star base pairs, and this T now normally would interact only with adenine. It would now interact with the other base pair, guanine and cytosine. So they can cross-correlate after that proton tunneling happens. And that is essentially mutation. You don't want that happening in your biological systems. And that's a spontaneous mutation. There's people in Oxford that can work out the theory of it, and there's work going on and experimentally verifying some of this. What do I have now? Okay, so to introduce the next interesting quantum phenomena that biological systems use, I want to engage you orally, and let's see if this works. I think we did have this turned on at some point. Does it work?
Yes, just put that switch. You need some help, let me know.
If I can turn it on. Here is the on button. Power. Click on. Okay, good. Alright, so I will just place this here and we'll hope that it works. And then I need the mallet. Okay, so I have two tuning forks here, pretty close in frequency. Okay, and if I hold one of them and then just everybody heard that?
Mm-hmm.
Okay, let's now try to get both of them to vibrate. Let's see if I get to do a good job. Then you should see some modulation. You see modulation, sound increasing and then dying down and increasing again and dying down. These are beats because these two tuning forks have very close frequencies, and then they add together at certain times and then cancel each other out, giving you this modulation in the intensity. Okay, that is called beat. So that's the oral thing. It turns out if you have two different pathways for light, this is what you saw there, what you heard there rather, is very similar to the interference that I showed you with light. Okay, very, very similar. So you had these two pure frequencies, and you got these large sound, and then it died down, came back again, and that's basically the phenomenon of beats. It turns out you can have quantum beats when you have transitions going on. Remember I told you energy exchange between matter and light happens at happens by following the laws of quantum mechanics. So I have a question here for you. This is a process of emission. Two starting points, but they end up in the same state. So these are electronic energy levels. Remember our quantum ladder of energy levels. And here I have slightly different. This is called a V-type atom, and this is called the lambda-type atom. And this is what I grew up with as a grad student, calculating properties of some of these V-type and lambda-type atoms. So the question I have is, in which one of these two pictures, or in both, you may say both, would you get quantum beats? Again, we're looking for interference. We're looking for some sort of a coherent wave-like behavior that when they're slightly apart in frequency, you should see this phenomenon of beats, where you get high amplitude and low amplitude. Any thoughts? Anybody? This one? V-type. Or V-type. V type. Somebody said V type. Okay. I have at least two who are supporting V type. Let's go with that one, right? Sometimes it's okay to go with majority. Though science, as you know, when you're doing science, that doesn't always work, right? Majority may not always be right. So let's see why that would be. So you want the common end state, really. Just like in the interference experiment, we had these two waves falling on the same screen. It's kind of like that. Here you can think about this in more or less the same way. The photon in an interference experiment had two paths to cover to reach the destination. Here, what I do is I excite these atoms, okay, so I provide some energy to them, so they end up in some kind of a combination of the state A and B. And once they're excited, they have two pathways to come down to the final ground state. And so both of these frequencies may be emitted, and you're going to get because the end state is the same, you're going to get beats. Here you don't get beats in emission, though it turns out there is interference happening there if you work with absorption, and it leads to very, very interesting scenario called electromagnetically induced transparency, meaning once you have one field present, you can actually control, you can actually control how the atomic transition responds to the presence of light there. Even if you have normally, when you have atomic levels like that, and you shine a laser that has more or less the same energy to allow the electron to do the jump, the light will be absorbed. Here, having this one present, we can actually shun absorption completely. We can cancel it completely using quantum interference, and you get something very interesting there. Alright, so quantum coherence is what is really going on here. When you have two wave sources, that's classical definition of coherence. We have two wave sources that are perfectly coherent. If they have sort of a constant phase difference and same frequency and more or less similar waveform, we want that to be stationary, meaning with time you don't want these wave properties changing, because then the interference pattern that I kind of showed you earlier with the demo, it will wash out if I didn't have a coherent source to begin with. You can't do that very easily with ordinary light source, for example, because from 1 second now to, let's say, 1 second later, it is not going to have that coherent waveform. It will be random, and that randomization washes out the interference pattern. And so this quantum coherence is a very, very fragile quantity. It doesn't stay there for very long. Normal systems, if you isolate the quantum systems, you're going to be able to maintain quantum coherence for very long, but no system is isolated, especially not in chemistry, not in biology. You're talking about room temperature, biological things, in aqueous environments, and so on. So it is really what's questioned quite a bit, why quantum coherence is coming at play there, and it turns out it is important. So one situation where it plays out is photosynthesis. And here you actually see quantum beats happening. The light that falls on the floating structure, very complicated looking, right? But we don't need to worry about that. All that is going on there is normally, you would have chemical processes going on at the femtosecond level and on the atomic distance scales. Now, when we're talking about photosynthesis, we're talking about macroscopic structures. Unless you have quantum coherence, and later on I will talk about entanglement at play, you cannot have things, which is these beads, surviving for about picoseconds and much bigger than, I should not have said atomic there, much bigger than atomic distance scales. And what is really going on here is, let me show you clearly on the next slide there. So, a variety of systems actually do photosynthesis, not just the leaves that you're familiar with. Marine algae and some bacteria also more or less follow the same mechanism. And it's not the process of photosynthesis itself, it's the primary first step that we're going to talk about. And what happens in this is, let me see, I think I missed one of my slides in the transfer from my old computer to this one. So let me show you quickly what goes on. So you have something called Okay, let me read through this, and then it will be kind of clear what is going on. So, fundamental biological process that provides energy for almost all life on Earth. Although a wide variety of organisms perform photosynthesis in different ways, initial stages of the process are essentially the same in all of them. And it's this initial stage that what we are going to talk about. It's basically this light harvesting process. Now, this light harvesting process is 100% quantum efficient. That means you give it one photon, that one photon is going to reach the reaction center where photosynthesis actually takes place. And that's amazing efficiency at systems that are working at room temperature. Could not have happened without quantum pathways. And what it turns out is these light harvesting process has lots of different proteins in it, and all of those pathways, remember we're talking about interference and pathways, these different pathways actually collaborate together to allow very quick and very efficient information transfer or the light transfer to the reaction center. And this is very, very interesting also with the creatures that live under the sea where there is extremely low light conditions. I'm not good with biological names, but let me see if I can recollect that. Phyto something, maybe biologists can help me. These organisms live under the sea, very, very under very dark environment. Phytoplanktons. Okay, so these phytoplanktons also, it turns out, use the same kind of idea, and single photon reaches where it needs to be. So let me now get to the next important property of quantum systems, which is related to the superpositions, being in two places at once. But now we're going from a single system to two systems, just to kind of keep things simple. So these two systems are kind of like family members. Now they are intimately attached to each other, but even when you separate them by several millions of miles, they retain these quantum correlations, and doing something to one, if you measure one of them, it immediately affects the other, immediately, instantaneously, without really any communication going on between them. And that is spooky. That's the deepest I'm going to go in this. Let me try to show you a possibility. So here there are two possibilities that are occurring. We're going to think about them as electrons, and I'm sure all of you here know electrons have spin up or down, or spin down or up. So the first picture here is the first particle, second is the second one. You have either that possibility up down, or you have the possibility of down up, and it's either one of those. But when you measure, you're going to have either this or that. That means if you measure the first one to be one up, the second one is immediately going to be down, and so on. And that's kind of how the idea works. Observed one affects over there the other way around. And so it has been done in the lab. I think Dr. Wong has these BBO crystals in his lab, and he could probably do this. He may have done this, I'm not sure. So you shine a UV laser on this BBO crystal, and out comes two photons, which are, one of them is horizontally polarized, the other one is vertically polarized. And if you look at the interface between these two cones, you have sort of a dichotomy, whether I have the first one horizontal or the second one horizontal, and so on. So you get these horizontal vertical 1, 2 versus vertical horizontal type of phase. Now, in the quantum technology world, this is very useful for quantum teleportation. Electronic states or states of quantum systems, even when you don't know what they are, can be transferred to a faraway location through the use of this entangled system as infrastructure or resource. And so without going into the details there, let's connect it with biology. The photosynthetic process, this is the picture that I was looking for earlier. So what's going on here is the light that's coming in, there are multiple pathways for it. This is where the light harvesting happens to some extent. The goal is for that light to reach the reaction center where actually photosynthesis is going to happen. And these multiple pathways somehow use that quantum coherence. One idea says they use this quantum coherence to figure out the quickest way to get to the reaction center, or the very recent understanding of this is there are 7 different type of molecules that exist in this protein complex that sits between the light harvesting complex and the reaction center. And it turns out the entanglement between all of these plays out in such a way that this happens extremely quickly and with 100% efficiency, very close to 100% efficiency. So there is quantum entanglement at play here in these macroscopic, life-size, room temperature systems. Pretty amazing, and only chemical bonds or molecules can do that. That is very, very interesting to study. And it's the next application, and almost the last one, about the magnetic navigation used by European robins. So, I don't know much about European robins. Some of you might. Tell me about it, and when we get a chance to talk. Very interesting birds, though. And let me see, there was a little. So let's now look at what is going on. So this is just my limit of knowledge of biology. It is interesting about this bird. There was that it's not just the magnetic navigation, but it's their vision, which is also a very important part of how this whole process works. And so vision system, we of course have to look at. There are these cryptochrome molecules that exist in the retina, over here, they're over there, and also in this, the two kinds of molecules that are sensitive to the light. They exist even in the human eye, called rod and cones. You may have heard about those, right? So these are just the rods and cones that are being amplified here, and some of the inner structure also shows cryptochrome molecules there and cryptochrome molecules in the outer layer of these rod cells. Okay, so it turns out this molecule is what is at play here, and when light shines on it, it creates a very, very interesting mechanism. Remember, we talked about these electron spins up and down. When light falls on one of these molecules, it actually creates separates, on one of the bond locations, separates the two electrons. And these electrons essentially then are entangled because they were part of a single system to begin with. The light is what breaks them apart, and they end up in either this up or down, oppositely correlated spins, or they could end up in the directly correlated, where both of them are pointing in the same direction. That depends on the initial condition, what sort of molecule you're talking about. So you either get this or that, and it turns out they are getting interconverted into each other continuously because of the spin coherence that exists in these molecules to begin with. Now what happens is chemically these two behave very differently, and that is what one takes the advantage of. So let me explain to you what the mechanism is. So this light photon coming in, that's coming in through the eyes of these birds. It creates these entangled photon pairs. Now entanglement does not live very long, and it doesn't have to live very long. But interesting thing happens is when you have electrons like that, more or less essentially free to move. Let me see if I can go back to my camera to quickly show you it is working. So let's. So I have a little top here. You may have played with it as a kid, and observe what the top does when I spin it. Okay. You can see the axis of spinning is not stable and vertical. It does this kind of wobble. Essentially, that's called precession. You get these electron spins and put them in magnetic field. They precess. Okay, and that's kind of what is going to happen. So this bird, when he creates, with the process that we talked about, when these two electrons are created, they continuously precess, right? And they are going to, depending on the direction of the magnetic field, these two electrons are going to precess differently. If they precess and from here end up in that situation, right? So initially they started here, but they end up in that situation, they cannot recombine anymore because the molecule doesn't allow that. That was not the stable initial condition to begin with. If you cannot recombine, that means they're not going to be able to come back to the same molecular structure that they began with. That means the energy that came from the light is completely absorbed, and that light then does not make it to the brain. That the signal from that light does not reach the brain. On the other hand, if the entangled pair, even after precession, depending on now the magnetic field direction, comes back to its original state, then they can recombine. When they recombine, the initially absorbed photon energy has to be given out. Now that sends a visual signal to the brain. So whether entanglement or not, which depends on the direction of the magnetic field, it then is translated into a visual signal that the Robins can then note down. And here is how simulation kind of shows. If they are looking north, this is what they see. It's kind of a curved, bright spot and dark regions here. And that the structure of this part changes depending on which way they are looking at. Okay, so that's for the north direction. If they are going southways, then that's how that works. So the presence of the magnetic field changes the entanglement structure and translates into the vision. Now, of course, we cannot see what the birds can see. So this is a simulation of what's possibly going on. And they have done actually some very remarkable and interesting experiments to really see if that works. So how do you mess things up, right? If you can mess things up, then you can tell, okay, you kind of understand what the mechanism is. And what they do is they apply RF fields, so trap these birds in a confined space, apply radio frequency fields, which would then mess up these electronic states. Now they cannot track the Earth's magnetic field, and they lose direction completely. They go in the direction that they would not normally migrate to. So something that has been experimentally figured out and understood. And so that is the role of entanglement at the macroscopic scale affecting the vision of the bird. And here is now a very last thing that I wanted to talk to you about, something that directly relates with my area of work, quantum optics, which is light matter interaction at the most fundamental basic level. If you did not know already, 2014 Nobel Prize was actually given for one of the ideas on the quantum microscopy, which is called super resolved fluorescence microscopy. So they use a very, very simple feature of light matter interaction, which I'm sure all of you have heard in your elementary physics classes, which is called spontaneous emission. Actually stimulated emission rather, where you have an excited atom and you bring in another light photon, and in the presence of this photon you actually can induce that excited atom to emit similar looking photon. That's what's predicted by Einstein. You can look it up, stimulated emission, and they use stimulated emission and one other very little trick. There are interesting states of light that can be generated. You can see the spot that this green laser is making on the screen. You have brightness in the center and then the brightness drops down. You can build laser beams, of course, after certain processing of this laser beam, where you have a tiny hole in the center, and you can make that hole small enough so you can actually, in some regions of where you are shining this light on, you can enhance spontaneous emission. Some regions you can suppress it. And that kind of allows you to make very careful sampling of the biological samples that you're trying to measure. And you can go essentially from optical light, which would allow, based on the Rayleigh criteria, which would allow you to measure things at the microscopic distance scales. You go to nanoscopy with the help of these little tracks. So you can measure these things which you would normally need, X-rays or UV rays to look at. Of course, when you're doing that to biological samples, you're providing more energy to them, you're killing them, and so you want to be able to see biological processes with optical light. And this is kind of the beginning stages. It allows us to do that. Again, pretty complex methods have come up since their early work. Just to kind of show you some of my work, again, that's the only slide with mathematical equations. A theoretical physicist cannot have at least one slide with equations, right? So this is what the standard microscopy tells you. You can see things about 220 nanometer with a green laser like this. The Nobel Prize winning work, they can manipulate the resolution by adding this extra factor in. And the very simple mathematical difference, the factor that they add in, or which multiplies this, in microscopy it is called a filter function, which allows you to manipulate some small little things. So where you can go down up to 50 nanometers with this extra laser that's now coming in, and the power of the laser is given here in terms of this ratio. My work on this with manipulation of atom-light interaction properties, I get rid of the square root sign, and that gives me tremendous enhancement. With the same power that they were able to do, I can go to resolution from 50 nanometers to 10 nanometers. That means I can see 5 times smaller things now with these ideas. Or, if I don't have that much laser power to begin with much less laser power, I can get this 50 nanometer resolution, meaning I'm giving much less energy to these biological samples. That means they will live longer. And in principle, you could then make a movie of biology at the molecular level in action with these kinds of ideas. So that was my last slide. Thank you very much for your attention.
Go ahead. We have time for a few questions? Before we get to the award ceremony, anybody have a question?
No questions. That may mean 2 things, right? Either I made sense or I was completely obscure.
Well, can we get one more round of applause for our speaker? And now